Thank you.
We have the next speaker with us, Tong Shen from the University of Southern California. Take it away.
Okay, thank you. So where's the pointer? Okay, yeah, thank you. Hello everyone, my name is Tong. I'm a postdoc from Daniel Lidar's group. So for today, I will present an algorithm we have developed to simulate the dynamics of the open quantum systems classically using quantum Monte Carlo. So, oops. Okay. So to start with, I'll just give some motivations, like probably that has been taught like many times in my in the previous previous presentation. But like the reason we want to simulate the full-time dynamics of the open quantum systems is kind of twofold. First, it's kind of like in practice you could not completely separate like the system from the environment. So in principle, you have to treat all of the system as an open quantum setting. And another reason is that like we want to use some classical simulations to help us facilitate the quantum error correction because all of the quantum computers we have are noisy. And so we want to simulate the quantum circuit classically. And similar to the closed system picture where we have the Schrodinger equation in the open quantum setting, we have a master equation. So instead of evolving the wave function, we now try to evolve like the density matrix. So the first term is the unitary evolution driven by the system Hamiltonian, and then we have some dissipation term. So here, I just give some motivation of why we want to solving with QMC, given that there's already like two existing methods. First is the exact solution, which we call the quantum master equation. This approach is simple. So here I just present a very simple way of solving it. If you solve this differential equation to the first order, you can, and then if you vectorize your density matrix, this Liouvillean super operator now becomes a matrix. So like right now you have basic like matrix vector multiplication. And then like there are also tensor network approaches where you have a graphical representation of your cross operator, which would give you access to the open quantum system. But like these two methods have their corresponding drawbacks. So for the exact solution, we have a well-known curse of dimensionality, which is that the size of the Hilbert space grows exponentially as you increase the number of the qubits in your system. So here for the master equation, it's typically you can only simulate like 10-ish number of qubits, and for the tensor networks, like the bound dimension, which measures the computational complexity, this increases significantly if you include long-range interactions. So here to give an intuition why QMC can kind of circumvent these two major drawbacks, I just use some kind of arbitrary sparse density matrix as a representation. So here we just have some like sparse density matrix, and all of the black regions here, like they have some very small values, or they could be even zero. And most of the values are concentrated along the diagonal, but we have some off diagonal coherence. And for the master equation, like no matter how small these values in the black regions are, you have to treat all of the matrix elements uniformly, regardless of the sparsity. So here, if we can use some randomization to sort of like compress this density matrix, like in this quantum Monte Carlo terminology, not in this quantum Monte Carlo context, this means that we can, all of these black regions, they can be rarely visited or like are rarely sampled. And if we allow some biases in our system, we can even completely ignore all of those black areas, which can kind of cut this the growth of dimensionality in the case of the sparse system. And also, even though this may not be a very accurate representation, but like quantum Monte Carlo, they do not really care about the range of the interactions. So like all of the interactions, like regardless of the range, can be treated uniformly in the QMC framework. But definitely, there's no free lunch. So for QMC, it has its own problems, which we call it the numerical sign problem. So here we develop a method which is kind of well known in the quantum chemistry, which is called the full configuration interaction quantum Monte Carlo. It is originally proposed to simulate the ground state energy of some chemical systems. And the way they kind of negate the sign problem is that what they do is to use what they call a population dynamics by increasing. So by kind of increasing the population number, they can kind of negate the sign problem. And this method has been adapted to simulate the real-time dynamics of some closed systems, and then also be used to simulate the steady states of the open systems. So here, what we present is that we can kind of generalize all of these methods to compute the full-time dynamics of open systems using this populational, using this population dynamics. So for the sake of time, I cannot give a very detailed introduction, but I'll give you some sense of how the formalism of our algorithm is. So first, you want to randomize your density matrix. So first, you expand your density matrix into some bases, and then you have the coefficient. And then what you do is that you randomize your coefficient. You use some integer, what we call the population of the workers, to replace this coefficient. So like there are some integers, there are some unnormalized value. So you normalize it by sum over all of the diagonal elements to make sure that your density matrix, the trace of your density matrix is 1. So here, by using this approximate population form, you can then rewrite your master equation into a population dynamics equation. So here, you replace all of your density matrix in your master equation by some worker population. Because you approximate your unnormalized density matrix with some integers, you increase some, you have some added like a stochastic error term, and we have proven that at any time the expectation value of this stochastic error time is 0. So which means that this approximation is unbiased. And by increasing the number of workers, which also turns out to be the computational overhead of our algorithm, you can systematically reduce this stochastic error. So here, if you look at this matrix M, in the perfect case, if all of your matrix elements are real, which is definitely not true for the open quantum systems, but like in that case, you could imagine this one as some transition matrix in the Markov chain kind of setting. So here we just have two kind of motions. First, we call the spawn process. So which means that for any matrix elements, there are some they have some probability to generate a new worker into a new set, which depends on the elements of your supermatrix. And also for all of these on-site or diagonal elements of your super operator matrix, you have a so-called clone or death process, which means that if this value is positive, you have some probability of duplicate this worker. If it's negative, you have the probability of kill this worker. And one crucial step is that we have one crucial step to negate the sign problem is what we call the annihilation, which means that if you have two workers of different signs, and then which we denote by different color, and if they happen to generate two workers, like a pair of workers on the same site, we just annihilate. We just annihilate them, which means that we explicitly consider the sign problem at any time in our calculation. So here I'll just show some results. First is we do some simulations for the Markovian dynamics. The model we consider is the XYZ Heisenberg model. And then we choose our jump operator to be the spin-lowering operator for each site. So which means that each of the site is coupled to a spin-lowering noise channel, which tries to drive all of the qubits to the 0 state. And what we are measuring is the average site magnetization. And then we compare our results with the exact solution from the master equation. We just try two different cases. For all of our simulations, we set the dissipation rate gamma to be 1, and all of the other units are expressed in terms of the dissipation rate. So first, we try on the upper panel, we try the strong dissipation rate. So here, all of the interactions are kind of comparable to the dissipation. So in this case, the dissipation rate is kind of comparable to all of the interaction strengths. And we we do a 5-qubit case. This is our initial state. We prepare in the pure state and let it evolve. We can see a perfect agreement with the exact solution. And in the inset figure, we just plot the number of workers used in our system over the course of simulation time. And we know that because the Liouville operator is trace preserving, which is a very prominent feature in our algorithm, because in such case, we do not need to do any sort of population control as it did in other population dynamics, because all of the diagonal, because the sum of all those diagonal populations are always preserved by nature of this dual, by nature of the Liouvillean superoperator. As can be seen in this red line, it's always a constant. And then we have like the total number of workers that is increasing in this transient behavior. And it finally saturates as we go to the steady state. And then if we increase our interaction strength a little bit, we could see some more interesting phenomena. And we could also find a perfect agreement between the exact solution and the QMC. But in such case, because we have introduced more coherence in our density matrix, which means that we need more, like a larger number of workers to capture the dynamics of our system. So which means that like more coherence, like a larger computational overhead. And then to show that we can perfectly negate the sign problem is that we measure the phase angle of our measurements. So we could say that like all of those values, so like all of the phases of our observables are very small over the course of the simulation time. And then we could just wondering, there's a very promising feature of our method is that you can stop this QMC at any time, and then you can restart it with a new set of parameters. So this gives us a promising direction is that if we can simulate some non-Markovian dynamics. So we just use some very early results, which is that we try to design a quench protocol, and we're still using this XYZ Heisenberg model. But right now, like in the first half of the simulation, we do a closed system dynamics, which we initialize a system in a pure state and let it just evolve in the open quantum system, so which is a unitary evolution. And then at t equals to 3, we suddenly turn on the noise channel to let it like just go to the dissipation process. And then if we look at the number of workers in the inset figure, we could find that in the closed system, you have a rapid growth of the worker number. Okay, so which means that like it is actually really hard to simulate in the closed system dynamics and the open quantum dynamics because of the spread of entanglement. So here we also here we also did some performance benchmark where we could see that like the QMC still like they scale exponentially, but they are much faster. The Marx equation, and as a summary, like we have developed a population dynamics technique, and all of the features of the open quantum system actually makes it more efficient. And as an outlook, we want to generalize it to non-Markovian dynamics, and we have a package which we call the Hawkist. We want to fully integrate this QMC solver into this package. Okay, thank you.
Since we're running late,